In this topic we are discussing about operation of a transistor as an amplifier. Transistor can be operated either in the active region, or it can be operated in the cutoff region, or it can be operated in inverse active region or saturation region. Why the transistor is operating in 4 different regions? Because if we take the NPN transistor, we have 3 regions. This is emitter and base and collector. We have 2 PN junction. One is emitter base junction and the second one is collector base junction. These 2 junctions of the transistor can be biased in 4 different ways. This emitter base junction is also called as emitter junction, and this collector base junction, which is also called as collector junction, these both junctions can be forward biased, which we will call as a saturation region. The both junctions can be reverse biased, which we will call as cutoff region. This is cutoff. And the emitter base junction can be forward biased, and the collector base junction can be reverse biased, which we will call as active region. In order to make our transistor to amplify any electric signal, the transistor must operate in the active region. If the transistor is operating in the saturation region, the transistor simply acts like a short switch. It is like a closed switch. When you take a switch, this is an open switch, and when the 2 contacts are closed by using the pole, this is the closed switch. This is open switch. When the transistor is operating in the saturation region, it acts like a closed switch. Simply it acts like a closed switch. When the transistor is operating in the cutoff region, it acts like an open switch. In order to make the signal to amplify, the transistor should operate in the active region. So as the heading suggests, now the transistor is operating in the active region, that's why it can amplify the signal. What is active region? Here the emitter junction must be forward biased and the collector junction must be reverse biased. In order to make the emitter junction to be forward biased, we are connecting a battery VBB. This battery is connected between the base and emitter terminals, that's why we are calling this battery as a VBB. Sir, we are also connecting to the emitter terminal. Why we are not calling this battery as a VEE? Because here this transistor is connected in the common emitter configuration. As we already know, the transistor can be connected in 3 different configurations. One is common emitter, and the second one is common base, and the third one is common collector. How can we know whether this transistor is connected in common emitter or common base or common collector? We have to check the terminal which is common for the input and output. Here in this case, we are giving the input to the base terminal and we are taking the output from the collector terminal. In both the cases, we are not using the emitter terminal. So this emitter is common to the input and also it is common for the output. So this configuration is called as common emitter configuration. In the majority of the cases, in the next chapters also we will see, our transistor is always connected in the common emitter configuration. It is a very popular configuration. So in this CE configuration, the input is always given to the base terminal and the output is always taken from the collector terminal. So the input current is IB and the output current is IC. And the input voltage is VBE because the voltage I am measuring with respect to the emitter terminal. Output voltage is VCE because I am measuring this voltage with respect to the emitter terminal. And remember, I have not applied any input as of now. Assume there is no input. I have directly connected the battery. Because there is no input, there is no need to amplify. We are checking the condition, we are making our environment ready for the amplification. Before amplifying, we are checking whether transistor has the ability to amplify, whether it has the proper ground to amplify. In order to check that, we have to concentrate on input and output. Now the input is VBE, which is voltage we are giving to the base, which is a DC voltage. The battery we have supplied, whatever the voltage we are giving at the VBB is the input for the transistor. If the battery voltage is 5 volts, this is the input for the transistor. If the battery voltage is 9 volts, this is the input for the transistor. If the battery voltage is 12 volts, then that is the input for the transistor. So here we are giving the input, the battery voltage. So our first condition is satisfied. In order to make the emitter base junction forward biased, we are connecting this battery in between base and emitter terminals. As this is NPN transistor, the positive terminal of the battery is connected to the P region and the negative terminal of the battery is connected to the N region. So this emitter junction is forward biased. One condition is satisfied. And only the second condition which we have to check in order to make the transistor to amplify any electric signal is whether the collector junction is reverse biased or not. In order to make the collector junction reverse biased, we are taking the battery. You may get the doubt. We are representing the battery here with a simple anode and cathode, but here we are taking two batteries. Is there any specific reason? Yes, the specific reason is we are clearly mentioning that the voltage of this battery is much higher than the voltage of this battery. The voltage of this battery is making the collector junction reverse biased. Because of this battery, the collector junction is reverse biased, and because of this battery, the emitter junction is forward biased. Now the environment is set. Now we have the confidence that this transistor can amplify the signal. But where is the input? Now we are going to give the input. This state is also called as no signal state because we have not given any input signal. The current whatever we are getting, I am representing in the capital letters because this is a DC current. As this is DC voltage, this IB also DC current, output IC is also DC current. Whenever we are applying some small electric signal, that may be your voice, that may be any electric signal. But in order to amplify your voice signal should be converted to electrical signal first. Microphone does the task. Now the microphone is asking, give me your voice signal, I will convert to the electrical signal. Then we are giving to the transistor. Transistor is saying, yes, give me this electrical signal to me, I will amplify this signal. Now the electrical signal we have given. Sir, is there any guarantee that our voice signal is in this form? There is no guarantee. But why you are representing in the sinusoidal form? Because any signal can be represented as a sinusoidal. Who told sir? This is the statement by the Fourier. So he is saying, give me any signal in the universe, I will represent that signal in the form of the sinusoidal. Whether this is a fan signal or sea signal, ocean signal, or the signal which you get by walking, or the sound or noise or pressure or temperature, any signal in the universe, whether the signal is on moon or from the sun, whether the signal is from anywhere in the universe, if you get the signal, that signal if you give me, I can represent in the form of the sinusoidal. So that's why we are taking the sine signal and we are giving this electrical signal to the transistor. Transistor base we are giving this electrical signal. This signal is amplified. Now, whenever the signal amplitude is incrementing, the maximum amplitude of the signal is Vm and the minimum minus Vm. After amplification, signal is amplified. How we are saying the signal is amplified, sir? Without affecting the original shape of the signal, we are getting the same signal. But here, there is a phase shift of 180 degrees. This 180 degrees phase shift is observed because we have connected the transistor in the common emitter configuration. If we have connected in the common base or common collector configuration, there is no 180 degrees phase shift. So the signal is amplified, there is no doubt. But whatever the signal we are giving in the input, exactly it is appearing that the reverse of the signal is output. In generally, it is, we call technically, it is shifted by 180 degrees. Exactly, this is the 180 degrees phase shift output. This is the amplified output. We are receiving at the resistor. So this is how a transistor is operating as an amplifier. In the first case, when we started this concept, we discussed, we are revising the same basics. In order to make the transistor to amplify any signal, it has to operate in the active region. What is this active region? Transistor can operate in 4 regions. Or I can also say technically transistor can be biased in 4 ways. The both emitter and collector junction can be forward biased, and both junctions can be reverse biased. One junction can be forward biased and the other junction can be reverse biased. And the last one is reverse bias, forward bias. Out of these 4 cases, we will take the third case in order to make the transistor to amplify our signal. Now we are choosing this case. Our problem is now to make the emitter junction to be reverse biased and the collector junction to be forward biased and the collector junction to be reverse biased. In order to make the emitter junction to be forward biased, we are connecting the battery VBB. In order to make the collector junction to be reverse biased, we are connecting the battery VCC. And the battery voltages must be different. The VCC must be higher compared to the VBB. When we do not apply any input signal, the output signal is no signal output or zero signal output. When we apply the signal, this transistor is amplifying, but we are getting the 180 degrees phase shift output. This is how a transistor operates as an amplifier. This can amplify any signal. Only condition it is putting, give me in the form of electrical form, I will amplify the signal.